Hello everyone and welcome to this new episode for the STM32 tutorial, and today we continue our chapter for the clock discovery. So in the previous chapter we have seen how to understand and how to, to understand the clock system, and also how to read the data using a logic analyzer or an oscilloscope. However, in the case of you do not have an oscilloscope and you still would like to see what exactly the clock speed of your microcontroller, this episode is exactly for you. So in this episode, what we are going to see is, you see this number here that we do have is the value of the PLL speed and also the system clock. And we are verifying this with the logic analyzer within our microcontroller. So we are going to build functions that will give us the clock speed without the need of the oscilloscope or the logic analyzer. And this chapter comes in as the fourth chapter of our series, where we are going to build this support function that they will be very useful for the next chapters, and also even for the rest of the whole STM32 tutorial. So without waiting, this tutorial will have three main chapters. First of all, we need to update the new MCU because this is a different microcontroller than the previous episode, and this is done in purpose so we can see if you do have a different microcontroller, how you can adapt this, and that will be quite easy, straightforward, and simple to do. Then we are going to build a function which is called clock PLL, and this one will give us the PLL speed. And after that, we are going to build the function, the clock speed, which will give us the system speed. And by the way, all the code here is available on GitHub. You just need, if you're just interested to understand the logic and then apply it, please go ahead and do it. So the code is in the description. And before jumping, so we are going to use the board Nucleo F446RE, and the microcontroller is the STM32 F44RE T6U. And as a logic analyzer, we are going to use the oscilloscope Regal MSO5000 series. Okay, so that's all for the introduction. Without further ado, let's jump and start. Well, our starting point from code perspective is exactly the same code of the previous video, where we explored the clock system of the STM32. And this is the first part here. What I would like to do is change the microcontroller, and just to show you how to keep using the same code with a different microcontroller in the STM32F4 family. So this time, as I shared before, that's a different board. So this is the STM32F446RE, as I shared. And if I show the oscilloscope, let me bring the oscilloscope picture. Where's the oscilloscope picture? Here. The oscilloscope now, it's quite quiet because this is just coming from scratch. So we can't upload the code directly because the previous code, we had a different microcontroller. The code would be working, but we may have a gap in the memory perspective. So before loading the code, what you need to do is to go for this option for target and go for the device. And here you will be selecting in the search area. So let me hide the camera here. In the search area, you go for STM32 F446RET, and you get the TX here, and you click like this. So then you just go for the debug and check. You need to re-update everything. So you go for ST-Link, you go to setting, you see that the ST-Link is connected. It's also connected with the microcontroller. You need to reset and run. And also this one has been unchecked, so all is good. Okay, so let me bring this back here. Just save build again, just in case. Okay, and then I will load my code and see what will happen. So let me bring here and start loading, and we start seeing the microcontroller or the output coming. So it's a different microcontroller, but we can load the code. Don't forget, to choose again the code selection here, sorry, the device selection, and to load again. So that will be mapped at the right memory of the microcontroller. Good, that was the first part, just quickly to show you that we can use the same code on different devices. Then let's go for the next one, where we start building the first function to understand or to get the PLL clock. And the purpose of this one is that this function will not be able, so imagine you don't have your logic analyzer. So that will be extremely interesting to have those kind of data here. You will need a way to understand or to find how you can get the clock. And a way there is. So let's go back to our the STM32 cube here. And also here we need to change the STM that we are trying to check, but the logic is always the same. So STM32F446, and then I forgot the STM oh no, it was the wrong area, it should be here. So let's go F446 and then RE and then T6, this one. Okay, good. And you will see that the architecture is exactly the same. So we are not going to care about this. Those one are connections that we will not be using as a peripheral for now, and we will take a look later on about that. But from choice perspective, we are able to see the same logic going on. Okay, so let's go and see. So we do have the HSI, the HSE, we do have also the PLL clock. And those were the input that we are going to use. We can ignore this one for the moment because it's not really a part of the whole discussion we are going to make. Okay, but you can see that the MCO1, MCO2 are exactly the same. Okay, so let's start. And what would like to read initially, what should be the value of my PLL clock? So this is the initial value that we would like to check, is what is the value of the PLL clock. And if you take a simple logic, the PLL clock value will be whatever the input here, the HSI or HSE, and that PLL input value will be divided by this PLLM and then multiplied by the PLLN and then divided again by the PLLP. And this will give you the PLL clock. Okay? And to find this one, we are starting now building a function that will give us the PLL clock. So let's start step by step using the registers and everything to build this value. And this is useful if you do not have the logic analyzer. It will be very useful to understand how to track your clock value. Also, the other benefit of this, and we will see it further in the video number 4, is when you make changes within your clock, you need to track it here so you can have more control on what is connected, the peripheral connected to here. So that will help you to understand what's going on within the end peripherals. Okay, and if you do have question or this is not clear for you, just put me a comment and I'll be happy to discuss further this topic. And again, this code is available on GitHub, so just follow and try to understand. Okay, so let's start here, and we do have this one. So what we would like to return at the end is the value of a PLL clock speed. So let's call it int PLL CLK, and then we add a speed like this, and we put equal to 0, and at the end we would like to return it, this PLL clock speed. Okay, so let's hide here this one and make this one big because we don't need this one, and we start from here. So the first thing, and we jump again here, is to know what is my source. This is the initial thing that we can understand. So is my source the HSI or my source is the HSE? So to know that, there is a peripheral that we can, a register that we can use. So let's open here. And we do have not the data sheet, but we need a reference manual. And we have seen this before. If we go to the list of the registers here, and if we go on this one, no, not the CAR or the control register, we need to go to the PLL configuration. And on the PLL configuration, so let's check it, which one so let's see this one, the PLL source or the bit number 22, and here. This is the one, so the PL, if it's 0, then HSI is the clock selected. If it's 1, it will be HSE, it will be an external clock. So how we can bring this one to reality and to confirm which one is the right clock that we would like to get, then let's create this variable that we will call, bring this one here, and we call it int, and we call PLL source. Okay, this PLL source will be equal initially to 0. Okay, and what we can do on this one, we said if like this, and we check RCC and the PLL configuration, this one, the RCC PLL configuration, and we go here and we say the bit number 22 together. So if it's positive or if it's equal to 1, this end here, what is happening? So something is not right. I forget the parentheses. So if this one, the PLL source will be equal to the HSI clock speed. But now the HS, actually not the HSI, the HSE, the external, if it's equal to 1 means equal the external clock speed. However, now we do not know, that will be depending on the board and a lot of, this is something that we add to the microcontroller. This is not within the control of the microcontroller. But most of the board that we do have right now would have a very clear specification. So for example, we were able to read it. So let's go back and find this one. So the clock here, because we divided by 2, we had a division by 2 for the MCO1. So the clock is here is 8 megahertz, the external clock. And most of the board, the standard board that we do have in the market for the STM32F4 are 8 megahertz, beside the STM32F411 as external. So to make this one, let's open the clock.h here, and I prepared a certain snippet so we can have kind of a standard one. So let me put like this and copy here. So this one will check based on the microcontroller we are using. So the HSI clock speed, the internal one is always 16, so we do not have to worry about this one. As you can see, the HSI is always 16. But the external one, we can change here. And you can see right now, as we are using the F446, this one is 8, but the 411XE is 25, and this is because we do have for the blackboard, the small, the black pill would have a 25 megahertz input clock. Okay, so feel free to change this one based on your specific model. Okay, good. So let's close this one, not close it, let's keep it for the moment and bring this one here. Okay, so in case of HSI is used, we can define or take this one, so HSE. Okay, else we can select here. Let's open it here, and the PLL clock or the PLL source will be equal to the HSI clock speed, which is 16 by default. Okay, so now that all is good, so we got the source. Now we need to extract this PLLM, the PLLN, and PLLP to make the function and to get the value. So let's go and start with the first one. So to get those one, if I go back to here and go to PLL configuration, their value is hidden here. So we do have this PLLN here, the PLLQ is here, and also there is a PLLP. So let's show both. If I'm able to show this one and also show this one, so you can have a better idea between the connections. Okay, and actually the STM32F446R, this one have another input, the R, which is coming from here, but we are not going to cover this one within this tutorial because this is really an exception for the STM32F4. The other one will be working properly. So just for you to know. So you can see here, we do have the PLLQ, which is here, and we are not going to change it, but we do have the PLLM. The M is happening here, the N is here, the P is here, and we are now going to extract each one of them. So let's quickly, to cover this one quickly, I prepared also some snippet to get their position. Okay, let's go back quickly to the code, and those snippets are the position of each one of them. So let's take this one here, definition of them, and bring here. And you can see I didn't bring the M because the M is 0. So now let's start extract each one of them. The first one, let's get the P. Let's comment here, make it a little bit bigger, bring this one here, and we start by getting the P. The P is quite easy. So to get the P, we need also to understand what's going on inside it. So go here to the P. So for the P here, so 0, 0 means 2, 0, 1 means 4, 1, 0 means 6, and 1, 1 means 8. That's important. So the value is the binary value, and what we read is a little bit different. So let's go here, getting P, and what we need to do, so P, and let's add it here, so P, and then N, and also the M. Yep, let's this one. So P is equal, and we are going to take the value and multiply it by 2. So let's start with RCC, and that will be the PLL configuration register. And here we are taking as a hexadecimal 3, or even 3 would be okay. And we are going to push this one by the position of the P, which is 16, like here. And after that, we are going to put the whole thing between parentheses. So here we get the initial value, and then we add 1, and after adding 1, we multiply the whole thing by 2. And why we do this? Let me go back again and show you. So if it's 0, the value is dividing by 2, which means if this one is 0, so we add 1 and we multiply by 2. If this one is 3, we add 1, it becomes 4, multiplied by 2, it becomes 8. So we get our P value, and we are good. We just need to add this comma at the end. Then now we need to getting the N. The n actually is a different animal, a little bit more difficult. So let's go here. And for the n here, it starts from bit 6 to the bit 14. So we need to get this kind of how we get this one. So what I will do, and this is strategy here with a binary manipulation, I'll be creating a number which will have 1 from the bit 6 to the bit 14, and then make an AND operation and then shift it by 6 bits. Okay, so let's start with creating the number, and let me call it the N mask. Okay, so for the int I equal to 0, and then, no, actually not equal to 0, I would like to start it equal to 6, and I is less or equal than 14, because I would like from 6 to 14, we will have, and I need to get those two ones together, we will have an I++. Okay, and now I'm building my N mask. So my N mask will be like this. The N mask will be equal, it will be an or equal a 1 that has been each time shifted by I. Okay, this will build us the N mask, and then the N become quite very simple. So the N will be equal exactly to this RCC configuration register, and the N mask like this. And after getting this result, this is a little bit of binary thing that is happening. We need to shift the whole thing by 6 bits. Okay, easy peasy. Perfect. Then what we need to do, or we can use 6, or we can use our here, this snippet, the position of n. Okay, so we got the p, n, and the remaining one is the m. The m is quite straightforward because we already have, if I go back here, that's at the position 0, so it's quite simple, and we can put end here 3f. So let's go here and go for the m. M is equal, this will be the same thing here, and the hexadecimal 3f. Okay, so we got the whole thing. So what we need to do now is to get the PLL clock speed. This will be equal, and just follow clearly what I'm doing here. That will be the PLL source that we generated here, the PLL source, and we start always by multiplying, make the multiplication by n, like this. Keep all the multiplication one to the top, divided by here p multiplied by n. Exactly same as the formula. So let's go back here to the formula. The clock here, the PLL clock, will have the input that we got multiplied by n and divided by both p and m. Why I didn't divide first? Because sometimes this is this is integer, and the rest of the division will not be kept, and it can create a gap and a wrong result. Okay, so now we got everything, we got the whole function. We can take it and put it here, add it here. So this is the function, and we can start checking if we get the same result as what we do have in the system. So let's go here and we'll call int PLL value this, and we put equal to 0. Let's create here a while loop, And inside this while loop, we get this function clock PLL. I think the name, yeah, clock PLL is fine. So let's bring this one here, and we call the PLL value equal to the output of this one. Let's remove the void, and we will be monitoring this PLL value. Okay, so let's save, build. So there's no error, no problem at all. And let's load it then. Okay, and let's start our debug. So we start our debug for the moment to read the value of PLL. And to read this value, we just go here and click add PLL value to watch one. And we start running our code. So what we get here, and it's interesting, we do have a PLL value equal to 8. So something probably is working wrong. So let's put this one here. So now we are watching what's going on. And if we go to call local one and we check. So what we do have here, so the PLL clock speed equal 8, which is extremely strange for me, because if I check those values and I compare them, so my source is 16 because the HSI is selected, which is correct. And then I do have my P value equal to 2, my N value 192, so I'm extracting the right numbers, and my M value is 16. My N mask, we don't care, this is the N mask. And then we do have the PLL speed is 8, which is quite strange because if I go here, and I initiate the output 1 here and check the value. So if I check PLL clock, I should have 96. So something within the equation is not correct. And this is because, so I do have my PLL source. PLL source is equal 16, and then multiplied by 192, which is the N, which is correct. And after that, divided by P, which is 2. And exactly, this is the mistake. It's not N here, but M. That's the mistake. So let's go back again. And that was a live debug session, just for you to follow and to see what kind of mistake I'm doing. So I'm saving and building again. Then I am loading and going back again to the debug mode here. And if I go to the watch one window, I'm still having the PLL value for the test. And let's run. So let's run. And I have 96 as the value of my PLL. And to make things more interesting, so this is a 96, the value we got. Just the thing more interesting. And we need to check against this. So let's go back to our main code. And here, so we are having the PLL and just divide by 2 and to check if our value is correct or not. So let's check our oscilloscope. We go here and you can see the oscilloscope is oscillating between 50 and 47. And if we go to the STM32 and we check here divided by 2, not by 4, by 2, we have 48, which is almost the value that the oscilloscope is balancing between. Okay, so now we got the value of the clock or the PLL clock here. It makes our life much easier, and we can get now the value of the system clock. The value of the system clock is the selection between HSI, HSE, PLL clock. And to get this value and to understand where this is controlled, we can go to the RCC control register to create this one. So let's go for the RCC control register. We go here and on this one, the RCC control register, let's quickly check for this. Which one is it? The RCC clock register, or no, sorry, not the clock register, but configuration register. And this one, let's go here, the SWS, or system clock switch status. So there is two group of bits. This one, the first one here, the bit 1 and 0, this one is used to select. So we are not going to touch this one. But this one is the system switch that we are going to use. And this is the one that gives us the value. And for today, as I said, we are covering only these three ones, and the PLLR will not be covered for today. Okay, so let's go and back to our code. And here, so let's close this one, and we can start here building the next function. So let's close this one and start building this new function, which will give us the clock speed. Okay, so let's go here and start having our code. So let's take the value of the SWS, or the switch that we do have. So that will be the RCC, and we set the configuration register, and that will be the difference between, if I go back here, this one is between the bit 2 and 3. So to hide those, or to get only those bits from a mask, it will be a C hexadecimal. Okay, so and let's go here, and a hexadecimal C, and after that, together, we need to push it by 2 bits. So now we have our switch value. After that, let's have the int clock speed, CLK speed, which will be equal to 0 initially. And now based on this value, we can determine and get the clock speed. So let's quickly get this one. So if the SWS, or the switch status here, is equal to, let's create some snippets. This is something I created to make things more useful. So let's define this one here. So we do have the SWS HSI is equal to 0. So let's compare it again. If we go here and bring it to the end. So 0 HSI, 1 HSE, and 10 is PLL, exactly as this one. So if this one is equal to HSI, so if it's equal to HSI, then my clock speed will be equal to directly the HSI speed that we already set as a default, like this. And after that, we put in else. We just copy the same thing. We add it here, and instead of equal to HSI, now it's HSE. We bring it here, and then we can get the HSE clock speed, like this. Okay, and finally, we can copy this one again. We bring it here, and instead of the HSE, now it's the PLL output. And surprise, surprise, that will be equal to the output of the clock PLN. Having this, we can now put the return, and we are going to return the clock speed. Okay, so let's add this function here to the header function, adding here like this, and close one, and quickly go to check it. So here, let's call a CLK clock speed. This one or already exists, so I'll put it by clock, system clock. Okay, system clock, and will be equal to 0. Expected identifier. What did I put as a mistake here? Okay, I put this like this, maybe. Okay, that works. And now I will put this sysclock, like here, will be equal to the value of the clock system speed. Okay, and now let's have this one, and let's save, build, and load. We go to the debug mode here, and we can add the system clock speed to the value that we would like to watch here. And let's see it as a normal number. And let's run the code. Let's remove all this stop debug one. So now it says that my system clock speed is 16. And to check this against my against what's happening, we do have our logic analyzer. So let's quickly check it here. So instead of viewing the PLL here, we already prepared it. We can see in the MCO the system clock speed. We run it, and division, we would like 0 division here. Okay, I don't have the division 0. Oh, really? Let's call it 0. It's more, oh no, it's divided by 1. That make more sense to put it like this. Okay, let's save, build, and load. Okay, and if I take a look to the oscilloscope in the MCO2, the speed I'm reading here, this is a 16 megahertz. And you can see one of the things that's happening is that this is 16 megahertz dot something something, because the internal crystal of the microcontroller is really not accurate, not 100% accurate. But so far, that's exactly the same result. So the system here, let's go back again. I can know without having any logic analyzer that my speed or my system clock speed is a 16 megahertz, as you can see here. Okay, so that was all for today, and hope you enjoyed it. In the next episode, we will start changing the clock speed and unleashing the whole power of the microcontroller. So if you enjoy this one, I'm really happy you watch this whole episode, and see you soon. Take care. Bye-bye.